Okay, here's a video solution to this 1995 kind of spring oscillator collision problem. So this is going to review both linear momentum and energy in collisions, and also a little bit of harmonic motion. Alright, so as shown above, a 0.2 kilogram mass is sliding on a horizontal frictionless air track with a speed of 3 meters per second. When it instantaneously hits and sticks to a 1.3 kilogram mass initially at rest on the track, the 1.3 kilogram mass is connected on one end to a massless spring, which has a spring constant of 100 newtons per meter. Okay, so I'm going to call this the mass of A. I'm going to call this mass of B. So we're told mass of A, 0.2. Mass of B is 1.3. Velocity of A initially is 3 meters per second. Velocity of B initially is 0. And the spring constant is 100 newton meters. And we're told it's frictionless. So here's all of our information. So part A, we're to find the linear momentum of the 0.2 kilogram mass. So A. Okay, so just A. So this is just the mass of A times the velocity of A. Okay, so 0.2 times 3 meters per second equals 0.6 kilograms meters per second. And 2, ask for the kinetic energy. K is equal to 1/2 mv squared. So this is 1/2 times 0.2 and 3 meters per second squared. So this cleans up a little bit.
That experiment, I love that one. That little lab you did.
Right, and 3 squared is 9. So this cleans up to be 0.9 joules. This is our initial kinetic energy of our block 1, or block A. Okay, now B, we're doing a similar thing, and we're looking for the momentum of the combined masses. So once, this is after they collide. So they stick together. So this is a perfect inelastic collision. Okay, well, for part 1 here, what is the momentum? Well, remember that this was initially at rest. So the initial momentum of this entire system is equal to the momentum that we found right here. So the final momentum is still equal to 0.6 kilograms meter per second. And so that is going to equal the addition of our two masses, because now they're moving together. So we need to add their masses, and luckily this is pretty easy arithmetic. 0.2 plus 1.3 is 1.5. Okay. So, actually, my apologies. So, the answer to part 1 is just this. Okay, I was actually starting to solve part 2. Okay, part 2, we're looking for the kinetic energy. So, this is where I was alluding to over here. In order to get the kinetic energy, we need to get the velocity. Okay, so the velocity of those two moving together is our momentum. Divided by 1.5. Okay, and we should just expect this velocity to be smaller than the velocity of them moving together, of the first one moving separately, right? Because now there's more mass that's moving, and this is just 0.4 meters per second. So now this is still part 2. The kinetic energy is 1/2, and then this is the mass of them added together, because that's what's moving. And then the velocity, which is 0.4 meters per second squared. Okay. And this equals 0.12. Alright, well, so what we can see here is that momentum is conserved, kinetic energy is not. Kinetic energy went from 0.9 to 0.12. So that remaining energy is mostly going to be thermal energy, alright, if you remember. So that means the thermal energy is the rest, which is, it doesn't ask this, but from a conceptual standpoint, the rest of that mostly goes to thermal energy. Okay, so we're going to change gears a little bit, because after the collision, right, it does move. We found the velocity, but they're actually going to oscillate. Okay, so our system here is going to move this way, and then this way, and then back and forth, over and over again. Okay, so we're looking at simple harmonic motion with a horizontal spring. So the way I'm going to approach this one is with energy conservation. So once again, energy is so important to understand. This makes so many questions very, very easy. So remember, this is moving, right, with that velocity that we found of 0.4. Okay, right now, this spring is at its equilibrium position. So remember, if the spring is in equilibrium, that means there's no spring force, so there's nothing resisting. There's no spring force, so it has no elastic potential energy. So what that means is 0.4 is going to be equal to its maximum velocity. Okay, so that also means that all of the energy the total energy is going to be equal to kinetic energy at this point. So at this point, we're looking at the maximum kinetic. And if we want to find out what the amplitude is, we're going to want to find the maximum elastic. Okay, because the maximum elastic energy is going to be when it is compressed at its most, right? So where the amplitude is. And that's what we're actually looking for in C. So using basic energy conservation, right? This is the way that I would approach this. So our initial was kinetic, and afterwards, after it's compressed, this is going to be elastic. So 1/2 mv squared, 1/2 k. And then if it is the maximum, then it's, you know, it's not just x, it is the amplitude. So this is a squared. That's what we want to call it. Okay, so we're looking for the amplitude. Our 1/2s are going to go away. And we will divide by k, divide by k. So I'll rewrite this now. A squared is then equal to mv squared over k. So now we need to take the square root. So then A is equal to the square root mv squared over k. Okay, so now we can plug this in. Remember the mass is 1.5 because they're moving together. We found the velocity to be 0.4. That is squared. And the spring constant was given to us as 100 Newton meters. And this equals 0.049 meters with a little bit of rounding. So there's your amplitude. That's part C. The final thing, D, is asking us for the period. So what is the period of this spring? Okay, so this formula is given to you on the AP sheet. 2 pi m over k. So there's no algebra that we need to know, that we need to do here. We know the mass, and we know k. So, you know, sometimes the last part of the question is actually the easiest. It's 1.5 kilograms divided by 100. And this cleans up. You should get something about 0.77 seconds. Alright, there we go. Not too difficult. A good review of energy conservation and momentum conservation. All right. Thanks for watching.